Massive blocks of granite were cut with a precision that defies logic. This is the enduring enigma of ancient engineering, a mystery carved in stone that challenges our entire historical timeline. By the end, you will understand the startling theories that attempt to explain the impossible. How did cultures across the globe shape this brutally hard rock as if it were soft butter, leaving behind monuments that our modern tools struggle to replicate? What does their silent mastery reveal about forgotten chapters of human ingenuity? When you see the perfection of a stone joint so tight, not even a hair can pass, what does it make you question about the past we think we know? The ambition itself is breathtaking, a declaration in stone that echoes across millennia. To truly grasp the mystery, you must first understand the staggering scale of what was attempted. Think of the unfinished obelisk in Aswan, Egypt, still lying in its ancient quarry. This single shaft of red granite, had it been freed, would have stretched taller than a 10-story building and weighed well over 1,000 tons. It is a project of almost incomprehensible magnitude, abandoned not for lack of will, but perhaps because the stone itself cracked under the immense stresses of its own creation. This is not an isolated feat. Across the globe, from the Andes to the Nile Valley, ancient builders chose granite not in spite of its difficulty, but because of it. At Pumapunku in Bolivia, you find blocks of this stone cut with geometric precision, featuring notches, channels, and surfaces so flat and smooth they seem machined. Deep beneath the sands of Saqqara in Egypt, within the Serapeum, rest colossal granite boxes, each weighing dozens of tons, placed inside tombs with interiors polished to a mirror finish. The common thread is a material that defies casual effort. Granite is not just hard, it is brutally unforgiving. Formed from molten rock deep within the earth, it is a conglomerate of minerals like quartz, feldspar, and mica, each with a different hardness, locked together in a crystalline matrix. This is what makes it so durable and so devilish to work. Even with today's power tools tipped with industrial diamonds, cutting and shaping granite is a slow, deliberate process that generates immense heat and wears down blades rapidly. So when we look at these ancient monuments, the first and most fundamental question arises from pure physics. Given the tools we have historically attributed to these cultures, primarily stone hammers, copper chisels, and abrasive sand, how does the evidence before our eyes align with the presumed methods? The scale of the achievement immediately suggests that our standard narrative might be missing a few crucial pages, inviting us to look closer at the stone itself for clues left behind by the hands that shaped it. That polished surface tells a silent story of its own. If you were to examine the interior of one of those massive granite boxes in the Serapeum, or run a finger along the flawless curve of a perfectly shaped block at Pumapunku, you would find a startling forensic detail. In many of the most precise examples, the stone bears no visible tool marks. Under magnification, the surface reveals a consistent, almost glassy finish, devoid of the expected scars from pounding or chiseling. This absence is a profound clue, a quiet contradiction that speaks volumes. When we replicate ancient techniques using the tools we believe they had, the stone tells a very different tale. Experiments with copper chisels on granite produce shallow, messy gouges and quickly dull the soft metal. Using dolerite stone hammers or pounders to shape granite creates a distinctive pockmarked texture, a surface dimpled with countless small fractures. These marks are found in quarries, on unfinished works, and on rougher construction elements, but they are conspicuously missing from the finest finished surfaces. This presents our second foundational mystery. If the primary method was brute force percussion with stone hammers, where are the hammer marks on these perfect planes and complex interfaces? Materials scientists who have studied these surfaces often note something intriguing. The microscopic signature sometimes resembles that left by modern machining or precision grinding, not pounding. It suggests a process of material removal that was controlled, sustained, and capable of achieving a uniform finish. So we are left with a reflective question. Were the finishing techniques of these ancient artisans so advanced and patient that they could methodically erase all traces of their own rough work, spending countless hours with abrasives to polish away every imperfection? Or does this lack of conventional evidence point us toward a completely different principle of shaping stone? Perhaps they employed a method that interacted with the granite in a way that didn't rely on impact at all, a process that somehow allowed the stone to be worked rather than beaten into shape. This forensic gap in the evidence, this silence where we expect noise, pushes the mystery beyond simple effort and into the realm of potential lost knowledge. It suggests the story of how these stones were cut may not be written in the marks they left behind, but in the very consistency of the marks they did not. The traditional explanation offered by archaeology is one of immense patience and relentless human effort. It paints a picture of countless workers, their hands gripping simple tools, engaged in a slow war of attrition against the stone. The primary weapons in this theory are the dolerite pounder, a hard, dense ball of volcanic rock, and the copper chisel. The process is methodical, often called pecking and grinding. A worker would hold the dolerite pounder and strike the granite surface repeatedly, not to cut it in a single blow, but to fracture tiny crystals on its face. After an area was sufficiently bruised and weakened by this percussion, abrasive sand, often quartz which is harder than the granite's feldspar, would be introduced. By rubbing a piece of wood or stone back and forth with this abrasive slurry in between, the worker could slowly grind away the fractured material, grain by microscopic grain. This cycle of pecking and grinding, repeated for untold hours, could indeed shape the stone. The evidence for this is tangible. Archaeologists have found caches of these dolerite pounders in ancient quarries, their spherical forms worn down into egg-like shapes from constant use. Experimental archaeology projects have shown it is possible. Dedicated researchers using replicated tools have managed to carve grooves, shape blocks, and even create simple statues from granite, proving the method is fundamentally viable given enough time. This theory provides a comforting baseline, a narrative built from tools we have found and processes we can replicate. It speaks to the sheer willpower of ancient societies. But when we hold this proven method up against the actual artifacts, certain questions of scale and precision begin to emerge. The time required is staggering. Estimates suggest that quarrying and rough shaping a single large obelisk using these techniques could have taken hundreds of workers many months, if not years, of continuous labor. While this is plausible for a society with a large, organized workforce, it pushes the boundaries of logistical feasibility when we consider the sheer volume of precision work across multiple sites. More critically, the method struggles to explain the finest details, achieving the perfectly flat, mirror-smooth surfaces on the interior of a granite sarcophagus, or the razor-sharp, 90-degree internal corners found in some stonework, is extraordinarily difficult with a pounding and grinding technique. The process is inherently imprecise, and removing material from a tight internal corner with a round pounder or a piece of wood is a formidable challenge. Furthermore, the soft copper chisels, while perhaps useful for marking lines or working softer stones, would blunt almost immediately against granite, requiring constant resharpening or replacement. So while the pecking and grinding theory establishes a vital foundation of what was possible, its limitations in terms of time, precision, and tool efficiency are significant. It solves the mystery of how granite could be worked, but it leaves lingering doubts about how it could be worked so perfectly, on such a colossal scale, and with such apparent ease. This gap between the possible and the perfected is what fuels the search for other explanations, inviting us to consider whether these ancient engineers had access to a more sophisticated and perhaps lost understanding of their material. Perhaps the most compelling bridge between simple grinding and true precision lies not in a new tool, but in a new recipe. The concept is deceptively simple: a thick, gritty paste made from water and an abrasive powder far harder than quartz. This is the lost slurry hypothesis. Picture a wire saw used in modern quarries, a cable coated with diamond dust that slowly grinds its way through solid rock as water flushes away debris. Now imagine that principle scaled back thousands of years, using materials the ancients definitively knew. They had access to emery and corundum, natural minerals significantly harder than the quartz in granite. If these super-hard particles were ground into a fine powder and mixed with water to form a viscous slurry, the cutting potential changes dramatically. This abrasive paste, trapped between a saw blade, whether of copper, bronze, or even a tensioned cord, and the granite, would transform a simple back and forth motion into a remarkably efficient cutting action. Each stroke embeds millions of microscopic, ultra-hard grains into the relatively softer metal of the saw, creating, in effect, a continuous, self-renewing cutting edge. The slurry itself acts as both the cutter and the coolant, carrying away heat and stone dust to prevent glazing and keep the process moving. Machining historians often note the direct parallel to traditional lapidary work, where jewelers for centuries have used bow-driven drills with abrasive slurries to cut and shape the hardest gems. The evidence on the stones themselves offers tantalizing support. In some granite artifacts, particularly in the precise, flat-bottomed grooves meant to hold other stones or metal fittings, you can find a telltale signature. The grooves are often uniform in width and depth, with a surface texture that suggests a continuous, linear cutting path, not a chiseled or pounded one. Some even show the slight, consistent curvature at the ends that might indicate the sweep of a long, flexible saw. This method elegantly solves several problems. It explains the lack of hammer marks on finished surfaces, as the process is one of gradual abrasion, not impact. It accounts for the ability to achieve incredibly flat planes and tight internal corners, as a thin, rigid saw blade could reach where a round pounder could not. And it leverages mechanical advantage beautifully. A simple bow saw or a saw pulled back and forth by a team of workers could generate the sustained, reciprocal motion needed, turning human effort into a far more focused and efficient force. So the key question shifts. It is no longer just about whether they could cut the stone, but whether they had unlocked the secret of the slurry. Did ancient engineers discover that by suspending the hardest materials they could find in a fluid medium, they could, in essence, make the stone cut itself? This idea feels like a missing piece, a sophisticated understanding of material science that turns a simple grinding process into something resembling precision engineering. It suggests a level of technical refinement that goes beyond brute force, yet remains firmly within the realm of plausible, recoverable ancient knowledge. But even this clever hypothesis meets its own limits when confronted with the most baffling artifacts of all. But even the most efficient slurry saw runs into a stone wall of evidence, quite literally, in the form of small, circular holes. Scattered across ancient Egyptian artifacts, particularly on unfinished works and temple blocks, are the remnants of a drilling technology so advanced it has sparked debate for over a century. These are not simple pits, they are the negative spaces left behind by a process called tube drilling, and the cores they produce tell a story modern engineers struggle to read. The most famous example rests in the British Museum, a cylinder of granite about the size of a large drink can, extracted from a hole with almost surgical precision. To the untrained eye, it is just a piece of stone, but to a machinist, its surface is a detailed logbook, spiraling around the core from one end to the other, is a single, continuous groove. This groove is the fingerprint of the cutting process, a permanent record of every revolution the drill made as it ate into the granite. The consistency of this spiral is what stops observers cold. The distance between each turn of the groove, known as the feed rate, is remarkably uniform. It suggests the drill was descending into the stone at a steady, controlled pace, bite after identical bite. This is incredibly difficult to achieve with pure muscle power. Imagine trying to push a hollow copper tube into solid granite while also turning it, perhaps with a bow or a strap, and maintaining exactly the same pressure and rotation speed for hours. Your arms would tire, your focus would waver, and the groove on the core would show it with variations, hesitations, and uneven spacing. Yet on cores like the one in London, the groove often tells a different tale, one of machine-like regularity. So how did they do it? The basic mechanics of tube drilling are understood. A hollow cylinder of copper or possibly bronze would be fixed to a spindle. An abrasive slurry, likely that super hard corundum or emery powder mixed with water, would be poured into the cut. As the tube was rotated and pressed downward, the abrasive trapped under its edge would grind a circular channel into the stone. The tube itself would wear away, constantly being fed downward to expose fresh metal to the slurry, slowly sinking and creating a perfect cylindrical hole while leaving behind a solid core in its center. The shear force required is immense. Experiments have shown that to drill granite with a copper tube and abrasive, you need a significant and sustained downward pressure on the order of hundreds of pounds, combined with a rapid, steady rotation. This is the heart of the debate. Could a team of 2 or 3 people, using a large bow drill or a strap they pulled back and forth, generate and maintain these conditions long enough to drill deep into granite? Some experts argue yes, that with a cleverly designed capstone to bear the weight and a team working in shifts, human power is sufficient. They point to the minor variations that do exist in the grooves as proof of a manual process. Others look at the same evidence and see something more. They note that the feed rate on some cores is so consistent it suggests a mechanical means of applying the downward force, perhaps a weighted lever or a simple screw feed, to ensure the drill advanced automatically at a fixed pace regardless of the worker's fatigue. This would free the operators to focus solely on maintaining a smooth, fast rotation. The very existence of these drilled cores forces a profound question. Does this represent the absolute pinnacle of skilled manual craftsmanship, a testament to human patience refined to an art form? Or does it quietly point to a level of mechanical sophistication we have been reluctant to attribute to these ancient workshops? Perhaps the answer lies not in discovering a complex machine, but in recognizing a simple yet brilliant application of basic physics, a way to harness human effort through clever mechanics to achieve a result that looks for all the world like it came from a machine. This single piece of granite with its silent spiral challenges us to reconsider not just their tools, but their fundamental approach to solving an engineering problem. Yet even the clever mechanics of tube drilling cannot fully explain another persistent whisper from the past, a legend that speaks not of force or friction, but of transformation. Across continents and cultures, stories emerge of a different kind of mastery over stone, one that sounds less like engineering and more like alchemy. Spanish chroniclers traveling through the Americas in the 16th century recorded indigenous tales that spoke of a remarkable plant. They wrote that the juice from its leaves, when applied to the surface of hard rock, would cause the stone to become soft, almost like clay, allowing it to be shaped and molded before it slowly hardened back to its original, unyielding state. Similar threads appear in esoteric texts and local folklore from other parts of the world, hinting at a lost botanical or chemical knowledge, a secret formula that could temporarily disarm granite's crystalline defenses. This is the stone softening legend, and it offers a solution of elegant simplicity. It suggests the ancient builders did not cut the stone at all, but persuaded it to yield. The appeal is undeniable, painting a picture of wise artisans who understood the hidden properties of their natural world in ways we have since forgotten. It transforms the mystery from one of immense labor into one of profound, lost wisdom. But can such a story withstand the scrutiny of modern science? To answer that, we must ask what would be required to soften granite, even briefly. Granite's strength comes from its silicate structure, a tight, three-dimensional network of silicon and oxygen atoms bonded with metallic ions. To make it pliable, you would need to break those bonds on a massive scale, essentially dissolving the mineral glue that holds the rock together. Chemists who have examined this possibility point out the staggering challenge. There is no known plant extract or mild acid that can significantly alter crystalline silicate at ordinary temperatures within a useful time frame. Strong acids like hydrofluoric acid can attack silica, but they are extraordinarily dangerous, difficult to produce from ancient materials, and would likely leave obvious, corrosive scarring on the stone, a signature we do not see on the pristine surfaces of these monuments. Furthermore, such a process would be indiscriminate, affecting the entire treated area uniformly, making it difficult to achieve the sharp, precise edges and detailed carvings that are so evident. So from a strict material science perspective, the plant juice theory sits on very unstable ground, yet its persistence in the cultural memory is itself a fascinating clue. It may be less a literal description of a technology and more a metaphorical one. Perhaps these stories originated as a way to explain the unexplainable to later generations who could no longer comprehend the scale of effort or the sophistication of the actual methods used. When faced with a stone wall fitted together with impossible precision, it is easier to believe in a magical potion than to envision centuries of accumulated skill and relentless, organized labor. The legend fulfills a deep human need for a singular, lost secret, a key that unlocks all mysteries. It simplifies the complex tapestry of engineering, logistics, and artistry into a single, potent idea. In doing so, it reminds us that our search for answers is often intertwined with our longing for a past that held greater mysteries than our present. While the plant itself may be mythical, the legend underscores the true magnitude of the achievement it seeks to explain. If the reality was so astounding that it spawned tales of magic, then what does that tell us about the reality itself? This brings us to a threshold where folklore ends and the physical evidence presents its own, even more puzzling narrative. The legend of a softening plant speaks to a deep human desire for a singular, elegant solution. But what if the lost secret wasn't a chemical but a form of energy? This leads us into one of the most captivating and controversial realms of the mystery, the idea of sound. Across various traditions, from the high plateaus of Tibet to the deserts of the Middle East, there are persistent stories that describe stones moved not by ropes and ramps, but by song. Ancient texts and oral histories sometimes speak of priests or builders using carefully tuned instruments, trumpets, drums, or chants, to generate a specific sonic frequency that could, in theory, make massive blocks weightless or cause them to fracture along precise lines. The concept taps directly into a fundamental principle of physics known as resonance. Every object in the universe has a natural vibrational frequency, the pitch at which it most easily oscillates. You experience this when you push a child on a swing. A small, timed push at just the right moment, in rhythm with the swing's natural arc, creates a larger and larger motion. That is resonance in action, the amplification of energy through perfect timing. In a dramatic modern example, an opera singer can shatter a crystal wine glass by sustaining a note that matches the glass's resonant frequency. The sound waves transfer energy into the glass, causing its structure to vibrate until the stresses exceed its strength and it cracks. So the scientific question becomes, could this principle be scaled up to something as massive and complex as a granite block? Could a choir of voices or a bank of massive drums find the note of a 20-ton stone and use it to break internal bonds or counteract gravity? The energy calculations here are staggering. Granite is not a homogeneous material like glass. Its internal crystalline structure would dampen vibrations significantly. To induce a resonant state powerful enough to fracture or levitate a multi-ton block would require an immense and sustained acoustic energy source, far beyond what human lungs or skin drums seem capable of producing in an open environment. The sound levels needed would likely be lethal to anyone standing nearby. Furthermore, levitation via sound, while demonstrated in modern labs with tiny particles using ultrasonic standing waves, involves incredibly precise equipment to create zones of high and low pressure that can suspend an object. Scaling this to the size of a building stone with ancient technology presents problems that border on the insurmountable. So why do these stories persist, and what can they teach us? While the literal interpretation of sonic levitation may belong to the speculative fringe, the underlying idea is profoundly important. It represents a complete paradigm shift in how we think about ancient engineering. It moves the conversation away from the concept of a tool as a physical object you hold in your hand, and toward the concept of a tool as a controlled application of energy. It forces us to ask if we have been too linear in our thinking, imagining only levers, wedges, and abrasives. Perhaps the true sophistication lay in understanding how to manipulate forces, whether acoustic, vibrational, or even thermal, in ways that left no conventional tool marks behind. These sonic legends, whether metaphorical or based on a kernel of misunderstood observation, challenge us to expand our definition of technology itself. They suggest a world view where the boundary between science, ritual, and the natural world was far more fluid, where the goal was not to conquer the stone with brute force, but to harmonize with its intrinsic properties. Granite itself holds a clue to this line of thinking, one that is literally crystalline. Many of these ancient stones are rich in quartz, a mineral with a peculiar property. When you squeeze or strike a quartz crystal, it generates a tiny electrical charge. This is called the piezoelectric effect, a principle modern technology uses in everything from watches to microphones. Some speculative thinkers have taken this fact and woven it into a grander narrative. They propose that lost civilizations, perhaps like the legendary Atlantis, understood this property on a profound scale. The theory suggests they could harness the Earth's own natural energies, or even focus the power of the sun through massive, precisely cut lenses or crystal arrays. The goal, to generate a beam of concentrated thermal energy so intense it could soften or even melt the surface of granite, allowing it to be worked like warm wax. It is a vision of ancient power that feels both magical and technological, a bridge between myth and forgotten science. The idea is fueled by more than just quartz. There are curious archaeological finds like the so-called Baghdad batteries, simple clay jars that could have functioned as primitive galvanic cells, hinting at a very early, if isolated, understanding of electrical principles. Furthermore, there are mysterious stone surfaces at a few ancient sites that appear glassy or vitrified, as if exposed to extreme, localized heat. Could these be the scorch marks of a forgotten energy tool? To entertain the thought is to step into a realm where history meets science fiction. The practical challenges, however, are immense. Granite does not simply soften. It melts at a temperature exceeding 2,200 degrees Fahrenheit, a heat comparable to a blast furnace. Creating such a focused thermal point without modern lasers or plasma torches seems fantastically difficult. Even if one could concentrate sunlight with a giant crystal lens, the atmosphere scatters light, and maintaining a steady, pinpoint focus on a stone block for hours presents enormous engineering hurdles. More critically, there is a complete absence of direct evidence. No giant crystal lenses or complex energy-focusing machinery has ever been unearthed in an archaeological context linked to these monuments. The vitrified stones can often be explained by lightning strikes or later human activity involving fire. So why does this speculative vision hold such power in our imagination? It speaks to a deep-seated human intuition that the past may have contained peaks of knowledge that later crumbled into legend. When faced with an artifact that seems to defy the tools we have found, it is a short step to imagine tools we have not found, tools of light and energy, not just wood and copper. This line of thinking represents the outermost boundary of the mystery, where concrete explanation bleeds into mythology. It shows us that the gap in our archaeological record is not just a space for alternative history, but a canvas for our own awe. The very impossibility of the stones, in a way, invites the impossible as an explanation. It reveals less about the ancient world and more about our own relationship to the past, a longing to believe that human ingenuity once reached heights so profound they now seem like magic. And that longing forces a crucial grounding question. If we set aside the grandest myths of lost superscience, what does the actual, physical evidence, the stones themselves, the tool marks, the quarries collectively point toward? The spiral groove on a granite core hints at something more than skilled hands. It whispers of a guiding principle, a repeatable motion governed by mechanics rather than muscle alone. This leads us to a compelling and often overlooked possibility. What if the ancient solution was not a magical plant or a resonant frequency, but a sophisticated, yet entirely physical machine? Not a machine in our modern sense of steel and electricity, but one crafted from wood, stone, and bronze, a forgotten ancestor of the precision tools that would shape the industrial age. This is the forgotten machine tool hypothesis. It suggests that the true breakthrough was not in the cutting agent, but in the system that applied it with unwavering consistency. Imagine the Antikythera mechanism, that astonishing bronze artifact recovered from a Greek shipwreck. Its complex array of interlocking gears, designed to predict astronomical cycles, proves unequivocally that ancient craftsmen around 2,000 years ago were capable of conceptualizing and fabricating precise geared technology. If they could build a mechanical computer to model the heavens, is it such a leap to consider they might have built a mechanical aid to master the earth? The core requirement for machining granite is not overwhelming force, but controlled, sustained motion. A simple lathe, for instance, could explain the perfect cylindrical columns and symmetrical stone vessels found across the ancient world. By rotating a block of granite against a fixed cutting point, a copper tool fed with abrasive slurry, a team of workers turning a large wheel could generate the smooth, consistent surface finish that is so difficult to achieve by hand. The evidence lies in the symmetry itself, in objects that are perfectly round and uniform along their entire length, a signature of rotational work. But what about the enormous flat surfaces, the granite tables and box lids that are planar to within a fraction of a millimeter? This points to a different kind of apparatus, perhaps a milling frame. Picture a large, rigid wooden structure that carries a cutting head, a stone or metal blade embedded with abrasive on a guided track. This assembly could be pulled back and forth across a fixed granite block, or the block could be moved beneath it. The critical innovation is the guide system itself. With precise wooden rails or a screw feed mechanism, such a device could ensure that every pass of the cutter removed material at a uniform depth, transforming the erratic motion of human labor into a predictable mechanical process. This explains the repeatability seen at sites like Puma Punku, where multiple blocks share identical, complex profiles. They are not individually sculpted masterpieces, but components produced from the same template by the same machine. Power for such devices could have come from flowing water, animal treadmills, or even teams of people walking in a circle, converting simple rotational force into the linear or rotary motion needed for cutting. The machines themselves, built primarily of wood and rope, would have had a limited lifespan. They would have decayed, been repurposed for fuel, or simply fallen apart, leaving behind only their stone products as testament to their existence. This theory fundamentally shifts the debate. It moves us from searching for a singular lost secret and instead asks us to appreciate a lost engineering philosophy. It suggests that ancient builders approached granite not as sculptors, but as early production engineers. They may have designed systems to manufacture precision stone parts, focusing on the stability of the platform, the accuracy of the guide, and the efficient transmission of available power. This view grants them a sophistication we are only beginning to map through the silent geometry of their work. It presents a past where the line between monument and machine was beautifully and ingeniously blurred. The true marvel of ancient stonework is not found in the quarries but in the final assembly. After a block was cut, it had to fit, and here the evidence becomes almost unnervingly perfect. Look at the iconic walls of Cusco in Peru, built by the Inca. The stones are polygonal, a chaotic jigsaw puzzle of interlocking shapes, yet their joints are so tight that for centuries, observers have remarked you cannot slide a piece of paper or even the blade of a knife between them. This is not artistic exaggeration. It is a measurable physical reality. The same phenomenon appears half a world away in the granite boxes of Egypt's Serapeum. These massive sarcophagi, weighing dozens of tons, feature interior corners that meet at a flawless 90 degrees, with surfaces so flat they could serve as a modern machinist's reference plate. To understand why this is so astonishing, we need to think like an engineer. The concept is called tolerance, the permissible limit of variation in a physical dimension. When you build a simple wall, tolerances of an inch or two might be acceptable. The mortar will fill the gaps, but these ancient builders worked with tolerances measured in mere millimeters across surfaces that were many feet wide. Achieving such precision on a single, small block is a feat of skilled craftsmanship. Achieving it consistently across hundreds of multi-ton blocks, each with unique, irregular shapes, defies simple explanation. It implies a systematic approach, a controlled process from beginning to end. Consider the challenge of creating a perfectly flat surface without a precision straightedge or a spirit level. How do you know when the stone is truly flat? One ancient method might have involved the use of a surface plate. By coating a known flat stone with a colored paste or soot and rubbing a new block against it, the high spots on the new block would be revealed by where the pigment transferred. The stonemason would then grind down those high spots, repeating the process over and over until the pigment coated the entire surface evenly, indicating full contact. This process, called spotting, is still used in high-end metalworking today. It is slow, painstaking, and requires an immense amount of patient, repetitive labor. But it works. It could produce the mirror-smooth finishes we see. Now compound that difficulty, creating a perfect 90-degree internal corner, like those inside the granite boxes, is exponentially harder. You cannot easily rub one surface against another to check for fit. The corner itself becomes the measuring tool. The builders would have had to shape each of the three intersecting planes with incredible individual accuracy, trusting that when brought together, they would create that sharp, clean intersection. Any error in the flatness of one wall or the straightness of an edge would result in a visible gap or a rounded corner. The fact that these corners exist, sharp and true, suggests the builders possessed not just skill, but a profound understanding of geometry and a method for verifying their work that has left no physical trace behind. This leads us to a deeper, more reflective question. Was this obsessive precision purely functional? In earthquake-prone regions like the Andes, interlocking stones without mortar allow walls to sway and settle without collapsing, a brilliant example of seismic engineering. The tight fit prevents water ingress and eliminates points of stress that could cause cracking. But when the precision far exceeds what is necessary for structural integrity, when a joint is made seamless not just for strength, but for the sake of seamless perfection itself, it begins to feel like something more. Could this flawless fit have held a symbolic or even a sacred meaning? In cultures that saw their rulers as divine and their monuments as eternal bridges to the gods, a wall built without gaps might have represented a perfect, unbroken boundary between the earthly and the celestial. The stone itself, joined in perfect harmony, became a testament to cosmic order, a ritual of precision that was as much an act of devotion as it was of construction. The silent, seamless joints are therefore the ultimate evidence. They are the final, unarguable product of whatever methods were used. They tell us that the goal was not merely to move or to shape the stone, but to master it completely, to force it into a relationship of perfect alignment. This level of fit is a fingerprint of intent. It demands an explanation that accounts for more than just effort. It requires an explanation that accounts for an almost philosophical pursuit of perfection. When we stand before these walls and run a hand over a joint that has withstood centuries, we are not just touching stone. We are touching a standard, a benchmark of skill that quietly asks how a society without lasers or computers could possibly have set its sights so high and reached them. The seamless fit of those granite blocks presents a staggering achievement, but it is only half the story. Before a stone could be set with impossible precision, it first had to travel. Transporting these monoliths from quarry to construction site is a logistical puzzle that matches and perhaps even exceeds the mystery of their shaping. Imagine a single block of red granite weighing as much as 700 tons, the approximate weight of 2 fully loaded jumbo jets. Now imagine moving it, not with diesel engines and steel cables, but with ropes, wood, and human determination across miles of desert or river. This was the companion enigma faced by every ancient civilization that built in stone. The cutting technology, however advanced, was just one component of a holistic, highly organized system of engineering. To understand their genius, we must follow the journey of the stone. The most widely accepted theories paint a picture of coordinated, large-scale effort. For overland transport, the primary tools were likely wooden sledges. A massive block would be levered onto a heavy timber platform, and teams of workers would pull it forward with thick ropes. But dragging such a weight directly on sand or earth would create catastrophic friction, digging the sledge into the ground. The solution was both simple and brilliant, a testament to practical physics. Engineers and historians suggest workers would lay a temporary road of wooden rails or smoothed planks in front of the advancing sledge. More crucially, they would lubricate this track. Experiments and tomb paintings indicate they used water, or a slurry of wet clay, to turn the wooden rails into a slick, low-friction surface. With enough workers pulling in unison, sometimes numbering in the hundreds, even a multi-hundred-ton stone could be inched forward. An alternative or supplementary method involved the use of rollers, cylindrical logs placed beneath the sledge. As the stone moved forward, rollers from the back would be carried to the front, creating a continuous, moving pathway. The coordination required was immense, a rhythmic ballet of lifting, pulling, and repositioning that had to be perfectly synchronized to prevent the load from shifting and crushing someone. For truly monumental journeys, water was the ancient superhighway. The Nile River was the lifeblood of Egyptian civilization and its greatest engineering asset. To move an obelisk from the quarries at Aswan to a temple in Luxor or Heliopolis, builders would first carve a special, sturdy barge from dense timber. They would then use a network of canals to float the barge right up to the quarry face. Using levers, ramps, and perhaps the buoyancy of the water itself, they would carefully load the stone onto the vessel. The downstream journey with the current was the easier leg, but even then, managing a barge carrying 1,000-ton stone required incredible seamanship to avoid capsizing. The journey of the Lateran obelisk, originally commissioned for an Egyptian pharaoh and later brought to Rome by Emperor Constantius II in the 4th century, exemplifies this maritime challenge on an epic scale. It was hauled from Egypt across the Mediterranean Sea on a specially built ship, a voyage of over 1,000 miles that stands as one of the most audacious feats of Roman maritime logistics. Once at its destination city, the stone then faced the final, tortuous overland trek to its final resting place. Modern engineers have calculated the forces involved to better understand what these operations demanded. Moving a 700-ton statue, for instance, would require a pulling force equivalent to tens of thousands of pounds. This is not beyond human capability, but it requires optimal conditions, perfect leverage, and a small army of laborers. The true genius, therefore, may not lie in any single tool, but in the project management, organizing the food, water, and shelter for hundreds or thousands of workers, maintaining the tools and timber tracks, coordinating the pull teams with signal drums or chants, and planning the route around obstacles. This was a feat of administration as much as of muscle. It shows a society capable of long-term planning, hierarchical command, and the mobilization of resources on a state level. The cutting, the moving, and the placing were not separate mysteries, but interconnected phases of a single, monumental undertaking. When we look at a finished obelisk standing proudly in a temple courtyard, we are not just looking at a piece of carved granite. We are looking at the final product of a supply chain, a transportation network, and a labor system of breathtaking scope and efficiency. This logistical context completes the picture, forcing us to ask not just how they cut the stone, but how they conceived and executed a plan to move mountains, one back-breaking inch at a time. The immense effort of moving these stones only deepens the central question: why go to such extremes? Why choose the most stubborn material on Earth when softer, more workable stone was readily available? To understand the how, we must first listen for the why. For these ancient cultures, granite was far more than just a durable building block. It was a statement carved in the language of the eternal. In ancient Egypt, the answer shines as clearly as the desert sun. The prized red granite quarried at Aswan came from the very south, the direction associated with the origin of the Nile's life-giving floods. But more importantly, its color and enduring nature linked it directly to Ra, the sun god. The rosy hue of the stone was seen as the flesh of the deities, and its resistance to time made it the perfect vessel for the eternal spirit. To encase a pharaoh's remains in a granite sarcophagus, or to raise an obelisk to pierce the sky, was not merely an architectural choice. It was a theological act, an attempt to translate human ambition into a form that could withstand the ages and commune with the divine. The stone's difficulty was not an obstacle to be minimized, it was a feature to be celebrated. The harder the stone, the greater the demonstration of devotion and royal power, and the more potent its promise of permanence. This idea of stone as a living, sacred entity echoes across the world in the Andes. For the Inca and their predecessors, certain mountains, springs, and unusually shaped stones were considered huacas, embodiments of spiritual force. To build with granite was not to subdue an inert material, but to collaborate with a powerful essence. By fitting these living stones together with such reverence and precision, the builders were creating more than a wall. They were weaving a tapestry of spiritual relationships, anchoring their structures to the enduring power of the earth itself. The flawless joint was not just an engineering triumph, it was a symbolic seal, a perfect bond between the human and the sacred realms. In this light, the decades of labor, the generations of knowledge passed from master to apprentice, take on a different meaning. The work itself became a form of worship, a ritual as important as the finished temple. The blood, sweat, and years poured into the stone were an offering, transforming the monument into a testament of collective faith and perseverance. This perspective reframes our entire investigation. We have been searching for a lost technical manual, but perhaps the true secret was a sacred trust. The methods for working granite may have been closely guarded not just to protect a trade advantage, but because the knowledge was considered holy, reserved for priest engineers who understood its spiritual significance. The how was inseparable from the why. To carelessly reveal the techniques might have been seen as profaning the ritual, diminishing the awe that the finished work was meant to inspire for all time. The mystery of the cut stone, then, is layered. On one level, it is a puzzle of physics and ingenuity. On a deeper level, it is a window into a world where material and meaning were fused, where the greatest challenges were undertaken not in spite of their difficulty, but because of it. The silent, seamless granite stands as a permanent question. Did they conquer the stone, or did they learn to speak its language? Our modern world is built on a cult of speed, but the ancient engineers operated on a different clock entirely. The most profound ingredient in their recipe for the impossible may have been one we struggle to quantify: time itself. We are accustomed to projects measured in quarters and fiscal years, but the monuments that baffle us were often the work of lifetimes or even dynasties. A single pharaoh's reign could be dedicated to the quarrying, transport, and raising of one pair of obelisks. A temple complex might be expanded and refined over centuries, each generation of craftsmen building upon the refined techniques of the last. This timescale is not a footnote, it is the central stage upon which the mystery unfolds. It allowed for a socio-economic structure almost alien to our efficiency-driven mindset, one that cultivated not just workers but masters. In these societies, craft was not a job, it was a sacred lineage. A young boy might enter a stoneworking workshop as an apprentice, spending years simply mixing abrasive slurries or fetching water, all while watching, learning, and absorbing the rhythm of the work. His hands would graduate to pulling a saw, then to guiding a drill, and perhaps only in middle age would he be trusted to lay out the sacred geometry for a critical stone. His knowledge, earned through decades of silent observation and practiced repetition, would then be passed to his own son. This is the model of the medieval cathedral builder, where a family name might be associated with a guild for 10 generations, each adding a spire, a rose window, a flying buttress to a structure that would not be completed in their own lifetime. It is the tradition of the Japanese swordsmith, who might spend weeks folding and refolding steel, his entire being focused on the creation of a single, perfect blade, a process where spiritual discipline and technical skill become indistinguishable. Within such a framework, the concept of wasted time evaporates. Every stroke of the saw, every turn of the drill, was not a step toward a deadline, but a meditation in material. The granite was not an adversary to be quickly conquered, but a partner to be understood through years of intimate, patient dialogue. This accumulated, generational knowledge represents a form of technology in itself, a living database of techniques, tricks, and tactile understandings that never needed to be written down because it was embodied in the hands and eyes of the masters. So we must confront a grounding, humbling possibility. Could the answer be less about a forgotten machine and more about a forgotten mindset? Could these seamless joints and impossible precision be the product of applying simple tools, copper saws, stone pounders, abrasive sand, with a level of skill, patience, and accumulated nuance that our modern perspective can scarcely comprehend? It is a challenge to our own assumptions. We look for a complex key because the result looks complex to us. But to a master craftsman who spent 30 years doing nothing but polishing granite surfaces to a flatness measured by the smear of ochre paste, the result was simply the expected outcome of correct practice. The mystery, then, shifts from the stone to the society that could value such slow perfection. It asks us what we have gained in our age of speed and what we may have left behind in our relentless pursuit of the next thing. This view does not dismiss the ingenuity of their methods, but roots it firmly in the fertile soil of human potential, cultivated over spans of time we no longer deem practical. It suggests that the true lost secret might not be a tool, but the cultural patience to use it without hurry. Theories are compelling, but stone is unforgiving. To truly test how ancient granite work might have been done, you must get your hands dirty. This is the realm of experimental archaeology, where researchers roll up their sleeves and attempt to replicate the feats of the past using only the tools and materials they believe were available. Their workshops become time machines, and their successes and failures offer some of the most tangible clues we have. Perhaps the most famous of these experiments were led by the stonemason Roger Hopkins and the Egyptologist Mark Lehner, documented for television in the 1990s. Their goal was direct: to cut a block of granite using a copper saw and an abrasive. They constructed a large, wooden frame to hold a 10-foot-long copper blade, which teams of workers pulled back and forth like a massive ripsaw. Between the blade and the stone, they fed a steady stream of quartz sand mixed with water. The process was grueling. Teams had to work in shifts. The copper saw grew hot and bent under the strain, and the abrasive slurry was constantly draining away. Yet it worked. Over the course of several days, the team successfully sawed through a modest-sized block of granite. The cut was clean, and the experiment proved a vital point. The basic mechanics of using a copper saw with an abrasive slurry are absolutely viable. The stone can be cut, but the data from this and similar experiments also reveals a stark reality. The gap between possible and practical is vast. The experiment required a large, coordinated team, a purpose-built wooden saw frame that itself represents a sophisticated piece of engineering, and an enormous expenditure of time and labor for a relatively small result. The saw cut was also relatively slow and shallow compared to what would be needed for monumental work. Even more telling are the attempts at drilling. Researchers using copper tube drills with sand abrasives have managed to reproduce the distinctive spiral groove on a granite core. But to achieve a feed rate, the speed at which the drill descends, that matches some of the ancient examples, they had to apply hundreds of pounds of downward pressure while maintaining a rapid rotation. This often required the use of a weighted lever system, essentially a simple machine, to provide the consistent force that human arms alone could not sustain over hours. Without such an aid, the feed rate becomes erratic, and the spiral groove on the core shows noticeable variations, unlike the machine-like consistency found on some ancient artifacts. These modern replicants hit walls of fatigue, material limitation, and time that the ancient builders seemingly overcame on an industrial scale. The experiments provide a crucial baseline, a proof of concept for the simplest form of the abrasive theory. But they also illuminate the chasm between a successful demonstration in a controlled experiment and the mass production of precision granite components for pyramids and temples. They show us the sheer, staggering volume of work, but leave unanswered how that work was organized, refined, and executed with such flawless results, year after year, century after century. The silent testimony of the ancient stones seems to whisper of efficiency, a smoothness of process that our best modern attempts can only clumsily approximate. This gap between what we can replicate with great effort and what they accomplished as a matter of routine is where the mystery deepens from a question of technique into one of systemic mastery. Granite's secrets are not just historical, they are crystalline. To move beyond speculation, we must consult the stone's own language, the science of how it breaks. Geologists and materials scientists approach these monuments not as mysteries but as forensic sites. They ask a fundamental question: What does the physical evidence on the stone tell us about the forces applied to it? Their analysis introduces precise terms that help decode the ancient workshop. One key concept is conchoidal fracturing. This is the way glass or obsidian shatters, with smooth, curved surfaces and sharp edges. It happens when a material with no internal planes of weakness is struck with a concentrated force. Granite, being a mix of different minerals, does not typically fracture this way. Instead, it fails through a process called crystal cleavage. When struck, the individual mineral crystals within the granite, the feldspar, the quartz, the mica break along their own inherent weak planes. The resulting fracture is more ragged and irregular, which is exactly what we see on quarry faces and rough blocks shaped by stone pounders. This scientific observation confirms the use of percussion for initial roughing out, but it also highlights its limitation. You cannot achieve a perfectly flat, polished surface by randomly fracturing crystals. That requires a different mode of material removal, one that shears the crystals away uniformly, grain by grain, which aligns perfectly with the abrasive slurry theory. Another physical phenomenon often discussed is thermal shock. This is the stress caused by rapid, uneven heating and cooling. The method, known as fire setting, involves building a fire directly against a rock face and then dousing it with cold water. The sudden contraction causes the outer layer to crack and spall off. It was a well-known technique in ancient mining and quarrying, incredibly effective for softer stones like limestone or for cracking bedrock along a desired line. But its utility for precision granite work is highly questionable. Granite has a very low coefficient of thermal expansion, meaning it is remarkably resistant to changes in temperature. To induce significant fracturing through thermal shock would require an immense, sustained heat source far beyond a simple wood fire, followed by instant, total quenching. Even if successful, the process is violently unpredictable. It creates a heavily damaged, pitted surface full of microfractures, a far cry from the pristine, planar finishes on finished artifacts. More critically, thermal shock is a blunt instrument. It could never produce the smooth, flat-bottomed drill holes or the razor-sharp internal corners we find. The stone itself, as the material witness, shows no widespread evidence of the scorching and spalling patterns that fire setting leaves behind on the scale needed for fine work. This scientific perspective acts as a crucial filter. It gently sets aside the more dramatic ideas of stone softening or thermal slicing, not because they are unimaginable, but because the granite does not bear the forensic scars such methods would inevitably inflict. So what clues does the stone hold that point toward a plausible process? Under high-powered microscopes, the surfaces of these ancient cuts sometimes reveal a subtle, consistent grain. The individual crystals of quartz and feldspar appear to have been sheared or ground down evenly, their edges rounded off rather than violently shattered. This signature is far more consistent with sustained abrasion than with impact or thermal stress. It suggests a process that worked with the stone's hardness, wearing it down through relentless, controlled friction, rather than trying to defeat it through a single, overpowering force. This scientific grounding is not about diminishing the achievement, but about understanding its true nature. It shifts the inquiry from a search for a lost super technology to an appreciation of a mastered craft. The ancients may not have had our periodic table or our stress equations, but through generations of tactile experience, they developed an empirical, intimate knowledge of granite's behavior. They learned how it responded to the persistent bite of a hard grain dragged across its surface, how much pressure a copper saw could bear before bending, and how the sound of the cut changed as it reached the perfect depth. The language of science gives us the vocabulary to describe what they accomplished, but the accomplishment itself was written in patience, observation, and a profound dialogue between human ingenuity and the enduring heart of the earth. The tools we have found tell one story, but the stones tell another. Archaeology has unearthed a consistent toolkit from these ancient sites, primarily copper and bronze chisels, stone hammers made of dolerite, and simple measuring rods. These are the physical artifacts left behind, the tangible evidence of daily work. Copper, however, is a soft metal. On the Mohs scale of mineral hardness, where diamond is a 10 and granite sits around a 6 or 7, pure copper is only a 3. A copper chisel driven into granite would dull, bend, and deform almost immediately. Bronze, an alloy of copper and tin, offers a slight improvement in hardness but still falls woefully short of the material it was meant to shape. The stone hammers, while hard enough to bruise the granite's surface, are instruments of brute percussion, not precision, so we are presented with a fundamental disconnect. How do we reconcile these relatively simple, soft tools with the existence of artifacts that display machining-level precision? It is the central, driving tension of this entire mystery. If the ancient engineers possessed advanced technology, where is it? Why have we not found the hardened steel saw blades, the diamond-tipped drill bits, or the complex geared machinery that our modern intuition suggests must have existed? The silence of the archaeological record on this front is deafening, and it forces us to consider several logical possibilities. The first is simple economics and value. Specialized tools, even if made of superior materials, would have been incredibly precious. They would not have been casually discarded in a quarry or left at a building site. Like a master carpenter's favorite chisels, they would have been maintained, repaired, and passed down through generations of craftsmen. At the end of a project or the life of a tool, the metal itself would have been recycled, melted down, and reforged into new instruments or ceremonial objects. The most critical components of their technology may have been systematically reclaimed, leaving no trace for us to find thousands of years later. Another compelling possibility shifts our focus from metal to materials that simply do not survive the centuries. The true genius of their apparatus may have been in the frame, not the cutter. Elaborate wooden saw frames, intricate lathes built from timber and rope, complex pulley systems for applying consistent pressure to drills. These are all machines that would rot away to nothing within a few generations. A wooden guide rail that ensured a perfectly straight cut for 100 years would eventually turn to dust, leaving behind only the granite that it helped shape. Our search for complex machinery might be looking for the wrong thing in the wrong material. We imagine steel and gears, but the solution could have been crafted from acacia wood and hemp cord, engineered with a profound understanding of leverage and motion. This leads to the most abstract, yet perhaps most profound possibility. What if the primary tool was not a physical object at all, but a refined process, a body of knowledge so deeply ingrained it became instinct? The true technology may have been the accumulated, generational skill of the artisans themselves, a mastery passed from teacher to apprentice through decades of silent observation and practiced repetition. The tool was the knowing exactly how much sand abrasive to mix with water to create the perfect slurry viscosity. It was the learned rhythm of the saw stroke that maximized cutting efficiency. It was the tactile sense of when a granite surface had been ground to absolute flatness, a sense calibrated by a lifetime of hands-on work. This form of knowledge-based technology leaves no direct archaeological evidence, yet its results are etched permanently in stone. It represents a peak of human capability that our machine-dependent world has largely moved beyond, making it difficult for us to fully appreciate its power. This disconnect between the humble tools we find and the majestic artifacts we see is not a flaw in the mystery, it is the engine. It is what propels the investigation forward, compelling us to look beyond the obvious and question our assumptions about innovation and progress. The incomplete archaeological record is not a dead end, but an invitation. It asks us to consider that the past may have contained different paths to sophistication. solutions built from perishable materials and perfected human skill rather than durable metal and complex mechanics. The empty space in the excavation trench, where we expect to find the advanced machine, might instead be filled with the ghost of a master's intention, a blueprint executed not on papyrus, but in the disciplined minds and hands of a civilization that chose to build for eternity. The silent testimony of stone is not always about tool marks. Sometimes it is written in the shape of rain. This brings us to a theory that does not challenge how the granite was cut, but when and by whom. The controversy centers on one of the world's most iconic monuments, the Great Sphinx of Giza, carved from the bedrock limestone of the plateau. While not granite itself, the arguments it sparked send seismic waves through our understanding of all ancient monumental work, including the granite wonders we have been exploring. Geologist Dr. Robert Schoch, after examining the Sphinx enclosure in the early 1990s, proposed a startling idea. The deep, vertical, undulating weathering patterns on the Sphinx and its surrounding walls, he argued, were not caused by wind and sand, as mainstream Egyptology holds. To his trained eye, they were classic signatures of prolonged, heavy rainfall, water erosion on a massive scale. The climatic implication was profound. The last time the Giza Plateau experienced rainfall of that intensity and duration was at the end of the last ice age, around 10,000 to 12,000 years ago. If correct, this would place the Sphinx's initial carving thousands of years before the reign of the pharaoh Khafre, to whom it is traditionally attributed. The immediate and fierce academic debate that followed is well documented, but its ripple effect is what matters for our mystery. If the geological premise is accepted for the Sphinx, it forces a monumental question. What does it imply for the timeline of other, even more technically demanding structures, including those built from granite? The pyramids of Giza, which contain immense granite components like the King's Chamber and its soaring sarcophagus, sit on the same plateau. Could their foundations, or even their core construction, also belong to a far more ancient epoch? Proponents of a revised timeline point to subtle but puzzling details. They note the extreme weathering on the granite blocks of the so-called Valley Temple next to the Sphinx, which appears more degraded than one might expect for its age. They question the logistical leap required, suggesting that the sophistication of 4th dynasty Egyptian engineering seems to appear almost fully formed, without a clear, gradual evolution from simpler techniques. The water erosion theory, therefore, is not just about dating a statue. It is a key that could unlock a radically different historical narrative. It suggests the possibility of a lost cycle of civilization, a precursor culture with its own advanced understanding of stoneworking that flourished in a forgotten age. The monuments we attribute to known historical empires, in this view, might not be original creations, but later restorations, adaptations, or rebuilds upon a much older, more mysterious foundation. The granite boxes, the perfectly fitted walls, the obelisks, could be remnants of that first epoch, later claimed and emulated by the civilizations that came after. Mainstream geology and archaeology offer robust counterarguments. Critics of the water erosion hypothesis point out that the weathering patterns could be explained by a combination of factors, including wind erosion, the effects of chemical weathering from morning dew and groundwater capillary action, and even the possibility of the Sphinx being carved from a layer of rock with pre-existing weaknesses. They emphasize that there is no archaeological evidence, no pottery shards, no tools, no cultural layer to support human habitation or monumental construction at Giza that far back in time. The traditional timeline, they argue, is built on a converging web of evidence from pottery styles, radiocarbon dating of organic materials found in mortar, and the meticulous study of historical inscriptions. Yet, the very existence of this passionate debate is illuminating. It exposes a fault line in our understanding of deep history. It highlights how our interpretation of the past is often a story we assemble from fragments, and that changing one key piece, like the date of a single monument, can make the entire picture shift. For the mystery of the granite, this temporal expansion is crucial. It asks us to hold two possibilities in mind. The first is that our known ancient civilizations achieved these feats through a brilliant, concentrated explosion of ingenuity within the timeline we have charted. The second, more speculative possibility is that they were inheritors. The seamless joints and impossible precision might be the legacy of a much older school of engineering, its masters long gone, its methods faded into legend, leaving only their indestructible stonework as a challenge across the millennia. This does not simplify the mystery, it deepens it exponentially. Now we must wonder, are we studying the peak of a known civilization, or are we looking at the weathered footprint of a forgotten one? The echoes of stonework resonate across continents and oceans, inviting a wider view. To see if the mystery is singular or multiple, we must place the granite of Egypt beside the andesite of the Andes and the basalt of Mesoamerica. By comparing cultures separated by vast distances and time, we can search for a common engineering language or celebrate unique dialects of ingenuity. Let us construct a mental table examining three key columns: their approach to quarrying, their signature joint style, and the physical tool evidence they left behind. First, consider the act of extraction. In the Egyptian quarries at Aswan, we see a methodical, linear process. They cut trenches around massive blocks, then drove in wooden wedges that were soaked with water to expand and crack the stone free along a controlled plane. It is a technique of isolation and leverage. Journey to the ancient quarries of the Inca at sites like Rumacolca, and you witness a different philosophy. They often worked with the natural fracturing of the mountain, seeking out already partially separated blocks and using stone hammers to persuade them the rest of the way. There is less evidence of deep trenching and more of an adaptive, almost sculptural relationship with the living rock. Meanwhile, the Olmecs of ancient Mexico, famed for their colossal basalt heads, faced a different challenge. Their stone came from distant volcanic fields, and evidence suggests they used a combination of heating with fire and rapid cooling with water to spall off large boulders before shaping them. The quarrying methods alone reveal distinct personalities, one systematic, one adaptive, one thermal. Now look at the final fit, the joint. Egyptian granite masonry, especially in the Old Kingdom, often features large, rectangular blocks with flat, planar joints. Precision is achieved through that meticulous grinding and spotting process, resulting in seams that are tight and straight. Cross the world to the Inca walls of Cusco or Ollantaytambo. Here, the joints are not planar but polygonal. Each block is a unique, irregular shape that locks perfectly with its neighbors in a complex, three-dimensional puzzle. The precision is not in creating straight lines, but in crafting custom, interlocking contours. At a site like Puma Punku in the Tiwanaku culture, we see yet another style. The stonework there features not just tight joints, but blocks with precise geometric cutouts, recesses, and channels that look like components from a giant stone machine kit. The joint is not merely a seam, but an integral part of a complex architectural grammar. Finally, the tools. The Egyptian archaeological record is rich with copper chisels, dolerite pounders, and measuring rods. The Inca left behind countless stone hammers of various sizes. The Olmecs have yielded fewer specific tools, but the wear patterns on their monuments suggest the use of hard stone implements and abrasives. In each case, the discovered toolkit appears on the surface, inadequate for the task. This is the universal thread, the shared dissonance. Every one of these cultures, with their vastly different architectural styles, achieved results that seem to outpace the simple tools we have found in their ruins. They all faced the same material defiance, and they all found a way to answer it, leaving us with the same core question. So what does this global comparison tell us? It argues powerfully against a single, lost super-civilization seeding identical techniques worldwide. The styles are too distinct, too culturally fingerprint. The polygonal walls of Peru are an aesthetic and engineering choice utterly different from the rectilinear precision of Egypt. This suggests independent innovation, a testament to the universal human capacity for problem solving when confronted with stone. Yet the commonality is profound. Each culture, in its own way, mastered the control of fracture and the patience of abrasion. They all understood that to shape hard stone, you either guide its breaking with intelligence or wear it down with relentless persistence. The shared principle is not a secret tool, but a secret understanding, a deep empirical knowledge of material behavior passed through generations of craftsmen. The mystery, therefore, is not one phenomenon, but a series of brilliant parallel revelations. Different cultures sang different songs, but they all learned to harmonize with the mountain. This realization makes their individual achievements not less mysterious, but more magnificent, for it means the drive to build the impossible emerged not once, but repeatedly from the heart of human ingenuity itself. This enduring puzzle taps into something far deeper than academic curiosity. The mystery of ancient granite work is not just about stones, it is about stories, and the kinds of stories we choose to tell about ourselves. There is a powerful psychological allure to an unsolved enigma, especially one carved in such permanent, undeniable form. It creates a vacuum in our understanding, a space where imagination rushes in. For many, the standard explanations of patient grinding and immense manpower feel somehow insufficient, not because they are impossible, but because they lack a certain grandeur. We are drawn to the possibility of a grander narrative, a rewritten history where lost golden ages possessed wisdom we have since forgotten, or where otherworldly guides offered a helping hand. This longing speaks to a fundamental human desire, the hope that the past holds greater secrets than our textbooks contain, that there is more to our story than a linear march from primitive to advanced. This enigma serves as a perfect blank canvas for our deepest projections. In a world where so much is documented and explained, an ancient, unanswered question represents fertile ground for myth-making. It challenges a modern sense of human exceptionalism in a quietly profound way. The unsettling possibility is not that our ancestors were primitive, but that in certain arts of patience, material intimacy, and large-scale coordination, they may have achieved a mastery that our technology-dependent society has simply left behind. We can send probes to the moons of Jupiter, yet we look at a 3,000-year-old stone box and genuinely wonder if we could reproduce it with the same tools. That cognitive dissonance is thrilling. It forces a humbling reevaluation of what constitutes progress, suggesting that knowledge can be lost as well as gained, that a civilization's peak might be measured in seamless joints as surely as in silicon chips. This psychological layer fuels the mystery's enduring presence in popular culture. From best-selling books to countless documentaries, the granite puzzle is a cornerstone of alternative history because it provides physical, visitable evidence. You can stand in the Serapeum and run your hand over a surface that feels impossibly modern. That tangible reality makes speculation feel more credible. The mystery thrives because it offers a choice between two compelling narratives, one of human triumph through sheer will, and another of a forgotten chapter whispering of even greater heights. Often, the public imagination finds the latter more satisfying, not because it is more likely, but because it is more wondrous. A simple answer, no matter how true, can feel like a diminishment of the awe we experience when confronted by the artifact itself. We want the method to be as extraordinary as the result. This desire isn't about rejecting science, it is about seeking a story worthy of the stones, a narrative that matches the scale of our wonder. In the end, the silent granite asks us as much about our own need for mystery as it does about the techniques of those who shaped it. The gap between ancient mastery and modern capability is measured in microns and muscle. To truly grasp what was accomplished, we must watch our own best efforts struggle to keep pace. Today's stonemasons and engineers, armed with diamond-tipped wire saws, computer-guided milling machines, and hydraulic power, can certainly work granite. Yet when they set out to replicate specific ancient artifacts, a humbling pattern often emerges. The modern process, for all its noise and power, frequently stumbles where the ancient work glides with silent assurance. Consider the challenge of flatness. A team using a massive, computer-controlled granite saw can slice a block with impressive speed, but achieving a surface that is perfectly planar over an area of several square meters to the tolerance seen in an Egyptian sarcophagus lid is an entirely different matter. The saw blade, though diamond-hard, can deflect minutely under tension and heat. The granite itself may have internal stresses that release during cutting, causing the stone to warp ever so slightly after the fact. Modern artisans then spend exhaustive hours with large surface grinders and laser levels, painstakingly correcting these deviations, a process that consumes both time and expensive machinery. The ancient builders, it seems, achieved this flawless flatness as a matter of course, without any digital feedback or powered tools. Their method, whether an immense copper saw on a guided track or a relentless process of spotting and grinding, produced a result that our technology must work diligently to match. Intricate shapes present another profound difficulty. At a site like Puma Punku, stones are cut with complex geometric recesses, dovetail joints, and channels that intersect at perfect angles. A modern stoneworker using a diamond saw or a router can create such shapes, but the risk of fracturing the stone at a critical moment is ever present. Granite is brittle, and the vibrations from high-speed tools can propagate tiny cracks, especially near sharp internal corners. The ancient pieces show no such stress fractures. Their intricate details are crisp and clean, suggesting a cutting process that was somehow more gentle, more controlled, perhaps because it was slower and generated less harmonic vibration. It was a dialogue with the stone, not a declaration of war. The most telling contrast, however, lies in the sheer scale of logistics. We can move a 700-ton stone today, but we do it with custom-built transporters, dozens of hydraulic wheels, and a small army of traffic controllers. The project is a spectacle of modern engineering, documented and celebrated precisely because of its extraordinary complexity. The ancients moved many such stones, and they did so as part of a routine construction schedule. Their achievement was not the occasional marvel, but the standard operating procedure for an entire civilization. This is the quiet heart of the mystery. It is not that our science cannot explain how granite is cut, or that our machines cannot eventually produce a similar result. The unsettling truth is that they did it with what we perceive as profound limitations, and they did it with a consistency and elegance that still gives pause to the masters of our own age. Their work stands not as a primitive precursor to our technology, but as a parallel achievement of a different kind. It forces a question that resonates beyond quarries and temples. What does it mean for a society to direct its collective genius so single-mindedly toward a goal that offered no immediate practical return, only a promise of eternity? The stones are not asking us to find their lost tools. They are asking us to understand the culture that considered such perfection a worthwhile pursuit for generations. The most sophisticated tools can vanish without a trace, but the knowledge to wield them is even more fragile. If the methods for working granite were indeed a pinnacle of empirical engineering, a craft honed over generations, then their disappearance presents its own enigma. How does a civilization preserve such intricate, hands-on mastery across centuries without the safety net of detailed blueprints or instruction manuals? The answer lies not in stone, but in the silent curriculum of human tradition. In a world before widespread literacy, knowledge was a living thing, passed from mentor to apprentice through a language of gesture, rhythm, and shared experience. A young initiate in an Egyptian stoneworking guild would learn not from a textbook, but by standing beside a master for years. His education began with the feel of different abrasive sands between his fingers, learning their grit by touch. He memorized the sound a copper saw made when its stroke was true, and the subtle change in pitch when it began to bind. The correct amount of downward pressure on a tube drill was not measured in pounds, but in the tension of the shoulders and the resistance fed back through the wooden spindle. This was knowledge encoded in muscle memory and sensory intuition, a continuous chain of imitation and correction that could stretch unbroken for 100 generations. The techniques were likely guarded within secretive guilds or families, treated as sacred patrimony. To share them outside the lineage would have been unthinkable, a betrayal of the ancestors and a dilution of the craft's prestige and power. The how was protected not by locks, but by the slow, demanding rite of passage that was apprenticeship itself. We see echoes of this in other legendary lost arts. The formula for Greek fire, the terrifying incendiary weapon of the Byzantine Empire, was such a closely held state secret that it died with the empire that nurtured it. The method for forging the distinctive, watery patterned blades of Damascus steel, a process that involved specific ore sources and precise thermal cycling, faded when the Wootz steel trade routes were disrupted and the master smiths left no written records. In these cases, the technology was not impossible to understand. It was simply too tightly held, too dependent on a fragile human ecosystem to survive a major cultural rupture. This is the critical insight. The loss of such knowledge is rarely a single event, but a slow unraveling. A society endures hardship, a war disrupts the peaceful transmission of craft, a new religious or political order devalues the old ways, or a simpler, cheaper technology emerges. The master craftsmen grow old, and without a new generation of apprentices worthy of the trust, or in a world that no longer demands such perfection, their secrets retire with them. What was once a commonplace skill for a specialized class becomes, within a few generations, a legend. The techniques for working granite may have followed this exact path. As empires shifted and priorities changed, the immense economic and social infrastructure required to sustain such a high art stoneworking tradition simply dissolved. The quarries fell quiet, the wooden machines rotted, and the last masters took their tactile understanding to their final resting place. The monuments they left behind then underwent a strange transformation. From being testaments to a known, if elite, human skill, they became relics of a mysterious past. The how, once mundane to the initiated, now seemed magical because the living link to that knowledge had been severed. The stone remained, but the conversation between the artisan and the material had fallen silent, leaving us to hear only the echo of our own wonder in the empty space. A single flawless joint represents the work of a master's hands, but a city of such joints required the heartbeat of an empire. The true scale of the mystery becomes clear only when we step back from the quarry face and survey the civilization that surrounded it. Cutting granite with impossible precision was not an isolated act of genius. It was the visible peak of a vast, invisible socio-economic pyramid. The real wonder may not be the copper saw or the abrasive slurry, but the breathtaking human infrastructure that made their use possible on an industrial scale. Consider the logistical symphony of Old Kingdom Egypt at the height of pyramid building. To feed the army of laborers, artisans, and overseers, the state required agricultural surplus on a monumental level. Farmers across the Nile Valley, working fertile land irrigated by seasonal floods, produced far more grain than their local communities needed. This surplus was collected as a form of taxation, stored in vast granaries, and redistributed as daily rations to the workers' settlements near the construction sites. Archaeological remains at Giza reveal bakeries capable of producing thousands of loaves of bread daily, and vats for brewing beer, which was a dietary staple. The workforce was not composed of slaves, as outdated stories suggest, but likely a rotating core of conscripted farmers. These men would serve for a season when the Nile's flood made their fields untouchable, a period when their labor could be directed by the state toward monumental projects. They were housed, fed, and provided with medical care, an early form of a national labor project that exchanged seasonal service for the glory of the king and the gods. This system required a sophisticated administrative bureaucracy. Scribes kept meticulous records on papyrus, tracking everything from the number of copper chisels issued to a work gang to the daily bread ration for a crew of stone draggers. Overseers coordinated shifts, ensuring that the sawing of a granite block continued day and night. Specialized roles emerged, not just cutters and pullers, but men responsible for maintaining the wooden sledges, for mixing abrasive slurries to the correct consistency, and for navigating the barges that brought stone down the Nile. The materials themselves tell a story of far-reaching trade networks. The copper for tools came from mines in the Sinai Peninsula or possibly Cyprus, requiring secure trade routes and diplomatic relations. The high-quality abrasives, harder than quartz, might have been sourced from distant deposits of emery or corundum. Even the timber for the massive sledges and barges was largely imported, as Egypt had few large trees, necessitating trade with Lebanon for prized cedar. Every facet of this operation was interconnected. A disruption in the copper trade would slow the shaping of stones. A poor harvest could reduce the available workforce. The system's resilience depended on stability, centralized control, and a shared cultural purpose that deemed this staggering expenditure of resources a sacred necessity. From this perspective, the true technology behind the granite was not a secret tool, but social organization itself. It was the ancient world's version of a complex supply chain and project management software, all executed through human memory, written lists, and hierarchical command. The ability to mobilize, coordinate, and sustain thousands of specialized individuals over decades directing their efforts toward a single, generational goal was the foundational invention. The stone was ultimately cut by a society's collective will, channeled through a perfectly tuned engine of administration. This realization reframes our awe. When we marvel at a seamless granite joint, we are not just looking at a craftsman's skill. We are witnessing the final product of a farmer's harvest, a scribe's tally, a miner's toil, and a navigator's journey. The perfection in the stone is a mirror reflecting the perfected order of the society that produced it. It forces a humbling question about our own time. In an age of digital networks and instant communication, could we muster the same unified, patient focus to build something meant to last for 5,000 years? Granite yields to geometry, but it also bends to beauty. The most profound evidence of mastery lies not in the flat planes alone, but in the delicate curves and intricate symbols etched upon them. This is where the engineer's calculation meets the artist's soul, a fusion that elevates the mystery from one of pure mechanics to one of profound creative expression. To carve a detailed hieroglyph into a granite obelisk is an act of breathtaking confidence. It requires transitioning from the macro-scale work of shaping a 100-ton monolith to the micro-scale work of incising a symbol the size of your thumb, all on the same brutally unforgiving canvas. A single slip, a fraction of a millimeter too deep, and the error is eternal. How did the artisan achieve such control? The process likely mirrored the larger construction, but in miniature. After the obelisk surface was ground to a perfect, smooth plane, the artist would paint or scribe the design onto the stone. Then, using a much smaller, finer copper chisel or a pointed tool of even harder stone, they would begin to outline the symbols. But the copper alone would be useless. Here again, the abrasive slurry would be the true cutter. A fine paste of emery powder and water would be applied, and the craftsman would use a bow drill or a simple hand-held tool to trace the lines, grinding away minute granules of stone with each pass. The precision required is almost unimaginable. The depth of each cut had to be consistent, the edges of each hieroglyph crisp and clean, and the spacing between symbols perfectly uniform to please the eye and honor the sacred text. This was not brute force, it was the ultimate application of finesse. The hand guiding the tool had to be steady, the pressure constant, the rhythm unwavering for hours. It represents a pinnacle of manual dexterity and patience, a testament to the artisan's intimate conversation with the material. Look at the surviving obelisks like Cleopatra's Needle in London or the Lateran obelisk in Rome. Despite centuries of exposure, the hieroglyphs remain sharply defined, their forms legible and graceful. This durability is granite's gift, but the clarity is the craftsman's legacy. The same principle applies to the sculpting of granite statues. A block was first roughed out with stone hammers, then gradually refined with smaller tools and abrasives. As the form emerged, the serene face of a pharaoh, the folded wings of a deity, the tools grew finer, the abrasives more carefully graded, the touch more delicate. The final polishing stage would bring the surface to a luminous sheen, catching the light and making the stone seem almost alive. This seamless transition from quarry to masterpiece reveals the true nature of their technology. It was not a separate set of machines for rough work and fine work. It was a scalable, adaptable system of knowledge, the same understanding of how abrasives interact with crystalline structure, the same principles of controlled, repetitive motion, applied whether shaping a 200-ton sarcophagus or detailing the eyelid of a god. The artistic vision was not applied after the engineering was complete. It was embedded within the engineering process from the very beginning. The artisan's touch was the final, most refined expression of the engineer's method. This fusion forces us to expand our definition of their achievement. It was not merely about moving or cutting stone. It was about imposing human will and creativity onto the most resistant medium nature could provide. The hieroglyph is more than writing, it is a permanent vibration of intention, a thought made physically eternal. When we see these works, we are not just looking at what they could do, we are witnessing what they chose to say, with a clarity that has weathered millennia. The stone's voice was given to them by physics, but the words they made it speak were entirely their own. Perhaps the truth lies not in choosing one theory, but in weaving them all together. The granite itself does not tell a story of a single magical secret, but of a layered and brilliant process where each challenge was met with the most appropriate tool from a vast cultural toolkit. The ancient engineer was not a wielder of impossible technology, but a master of applied intelligence, selecting the right method for each precise step in a grand generational project. Think of it as a symphony, not a solo performance. The initial act, freeing a 1,000-ton block from the living bedrock, likely employed the raw, elemental force of thermal shock. Controlled fires built along a carefully marked line, followed by dousings of water, would exploit the stone's own brittleness, causing it to crack and spall along a desired plane. This provided the rough, raw material. Then, armies of workers with dolerite pounders would descend upon the liberated block, their rhythmic pounding not to shape it with precision, but to knock off major protrusions, to begin the long journey from a ragged mountain fragment toward a geometric form. This is the stage we see in the quarries, the stage of brutal reduction, but the transition from rough shape to perfect form is where the mystery deepens and where our synthesis becomes crucial. Here, the stone would move from the open quarry to the covered workshop, the domain of the master artisans. The granite block, now manageable in size but still weighing many tons, would be mounted onto a sturdy wooden bench or frame. This is where the simple machine enters the narrative, a large guided saw, a thick copper blade tensioned within a wooden frame, would be positioned above it. Workers would pull the blade back and forth in a steady, mechanical rhythm, but the true cutting agent would be the slurry fed continuously into the cut, a thick paste of water and crushed corundum, a mineral harder than any component of the granite itself. The saw frame provided the controlled, repeatable motion, the slurry provided the cutting teeth, and the generations of inherited knowledge provided the understanding of pressure, rhythm, and mixture needed to make the process efficient. For drilling, a similar synthesis unfolds. A copper tube is fixed to a spindle, but the spindle is weighted or attached to a lever to provide automatic, consistent downward pressure. A team uses a bow or a strap to spin the drill with rapid, even rotations, while an apprentice feeds the same super abrasive slurry into the hole. The machine ensures the feed rate is constant. The human power provides the rotation, and the abrasive does the actual grinding, together creating that eerily consistent spiral groove on the core. This integrated view respects every piece of evidence. It uses the tools we have actually found: the copper, the stone hammers, the evidence of fire setting. It incorporates the simple machines that would have left no trace: the wooden saw frames, the weighted drill guides, and it centers the irreplaceable element, the human skill, the tactile wisdom that knew how to listen to the stone, to feel when the cut was true, and to polish a surface to optical flatness using nothing but patience and a perfectly graded abrasive paste. This engineer was no alien visitor, but a brilliant problem solver within a powerful cultural system. The drive to build for eternity provided the motive, the organized society provided the logistics, and the accumulated wisdom of centuries provided the method. The answer to the mystery, then, might be beautifully, frustratingly human. It asks us to stop looking for a single lost key, and instead to admire the entire, intricate lock, a mechanism built from fire, stone, wood, copper, sand, and an incalculable depth of shared purpose. The silent granite has spoken to us across the ages, not with answers, but with a more compelling question. We have traced the journey from the sun-baked quarries of Aswan to the wind-swept heights of the Andes, weighing immense scales of ambition against the forensic whisper of tool marks. We have explored a full spectrum of possibility, from the pragmatic grind of stone and sand to the profound echoes of sonic legend. And yet, the central mystery of how ancient hands shaped this brutal rock with such impossible grace remains, in many ways, beautifully unresolved. That unresolved state is not a failure of our inquiry, but perhaps its greatest gift. It is an open invitation, a permanent crack in the wall of our assumptions about the past. This enduring enigma compels us to look upon these monuments not with the arrogance of modern hindsight, but with a genuine humility and a rekindled sense of wonder. It challenges the comforting, linear story we often tell ourselves about human progress, where knowledge only accumulates and old ways are merely primitive steps toward our own sophistication. The granite confronts us with a different truth, that peaks of mastery can rise in different eras, founded on different kinds of knowledge, and can even fade from memory, leaving only their magnificent, silent results. The ultimate lesson here may not be the discovery of a single lost tool or a forgotten chemical formula. It is a broader, more human recognition of what becomes possible when effort, time, and tradition converge with a singular purpose. These cultures demonstrate the boundless potential of focused human intention, channeled through generations. They show us that mastery is often less about a secret technology and more about the profound dedication to perfecting the principles you already understand, whether that is the physics of abrasion, the geometry of a joint, or the logistics of moving mountains. As we navigate our own world of dizzying innovation and planned obsolescence, the silent testimony of these stone masters offers a poignant counterpoint. They remind us that some achievements are measured not in processing speed, but in patience, not in disruption, but in continuity. A seamless granite joint is a monument to a different kind of genius, one built on the marriage of simple physical principles with an almost sacred level of collective dedication. So let these stones stand as a permanent question mark in the landscape of history, a reminder that the past still holds dialogues we have only begun to hear. If this journey through the mystery has ignited your own curiosity, we would love to hear your thoughts. Share your theories and reflections in the comments below, and subscribe to join us as we continue to explore the hidden, wondrous chapters of our shared human story.